and welcome back for a very short video, the last one on this module on solutions to the dispersion equation. We've described a number of techniques from the analytical, fundamental pulse solution. We've looked at particle tracking, random walks models. We've described the moments method for the spatial moments. We haven't really talked about the temporal moments, but we'll do activities about it. Now, finally, the last video lecture I want to do on solving the equation is finite difference. Now, this is going to be a very, very short video because we already did this in the groundwater cycle course where I really described, flow in aquifers and, how to find the head. And so I described the finite difference methods in some details there, so you can go back to that. That was the fourth topic. So video, 4.7 in the groundwater cycle course. I'm still including it here because obviously finite differences are very important, and most engineering models or most models that you would use in industry, in the back end or behind the scenes, they use finite difference and particle tracking to calculate, the flow field and / the mass transport, right? So finite difference is really important. And again, this is just a mud flow, domain where you can see like different materials represented by different colors. You can sort of see like veins here in the domain. So again, like little squares, right? Grids are really, so solving equations on grids is, the oldest method and still the one that is used, in industry to basically model flow and transport in aquifers. So again, this is just a very quick reminder because we went through all this, but if we look at what finite differences are, is essentially representing a differential operator, so d, some function, d, x or t, right? And represent it as a difference as opposed to a differential, so meaning, the function at x plus dx and the function at x minus dx, and this is f at those 2 points, divided, so the slope, essentially, this slope here, right, is just df over dx, right? So these are the values that we can use, right? So we can represent the differentials, right? Differential operators, so differential equations in the form of difference equations as opposed to differential, right? Just the difference of numbers. And typically what we want to know is what is the value of, the function at the next time step or somewhere else, right? So we just iterate through, we loop through time essentially to find, the solution at different times. So given that we know the initial one, then we can find the next one. So again, df dt here is just f at t plus 1, t minus 1 over 2 delta t, which we can approximate, as f at t plus 1 minus f at t, so now, because obviously t minus 1 sometimes we don't know when we start, divided by delta t. So it's exactly the same thing as the one below here. So this and this is the same, right? We just call t or x or whatever we want to call it at the bottom. So you can see that this one here and this one here are the same. And then the second differential can be approximated here. Again, the way we arrive at those approximations, I invite you to go back to those lectures in the first course, like I described exactly how we do the Taylor expansion and the approximations and how we actually find the difference equations for the differential equations. But right now, let's just use the results to represent, our advection dispersion equation, right? So we have advection dispersion. Here, let's say advection is 0 for now. We can represent C by difference here, right? So if this is dc dt, is C at t plus 1 minus Ct over delta t, okay? So here we're going to keep C at t plus 1, so j plus 1 here, t plus 1, on the left-hand side because that's what we want to know, right? We want to know what is the concentration at the next time step, and then in the next time step, and then in the future, eventually, okay? So we'll send C at t, right? So concentration now, we'll send it to the other side. So it's here. Actually, that should be a plus here. And then dispersion, right, is here, D. Now delta T, that's at the bottom, so when we change, we send it to the other side, it's delta T is multiplying D divided by delta X squared, so this is that second differential here, delta X squared. And then this is just this part here, so this is the value at the space before minus 2 times the value here plus the value, you know, at the next space. And again, this is in 1D, right? This is just considering X. So again, this is a little bit, maybe a little bit much to see. Again, this should be a plus here. But we can represent concentration at the next time, right, as a function of all things that are known, which is the concentration now, dispersion coefficient, you know, the time step, the space step in the X direction, and then the concentration at the next cell, previous cell, and 2 times the cell here. So all those things are known, so we can calculate the next time step, and the next time step, and the next time step, and that's how we can step through using finite difference. Just a couple examples. So again, this is in 2 dimensions. I'll get to talking about dimensions and boundaries in the next module in this course, right, coming up after this video. But just to remind you that finite differences are what we use to calculate head, right, everywhere. So you can see all those little squares that give head. Again, this is just particle tracking. We've talked about this. And here you can see a simple 2D domain that I did in MATLAB where you have a concentration. So if you have a pulse input right in the middle, you can see that over time it just grows, and you can see here that there's more dispersion in this X direction than in this Y direction. So there's dy, dx, right? So this is an anisotropic dispersion, right? There's more dispersion one way than the other, but you can see all those little squares in the background, right? So in the background, you can see that this is solved on a grid, right? On a mesh, if you will, of little squares, and that's, you know, using those difference equations or finite difference equations, we can actually calculate concentration through time and the evolution of concentration in our aquifer. Okay, thank you very much, and I'll see you in the next video.